Hello everyone, welcome back to my channel, and today we will together solve the problem related to the flattened binary tree to the linked list. We are given the binary tree and then we need to modify it to become looks like a linked list, because we need to return all the things in the root. It means that it still be the tree. However, we need to modify all the things in place. So just do the things like transform the way we reorder the nodes inside the root. So I see that there are so many approaches they use the stack. However, in here, I propose another approach, which we do not use the stack, but we still can result the same tree. For all of the binary tree problems, and then we also always need to define the base case and the recurrence relation. So this one is very important, not only for the tree, but also for the dynamic programming. So to learn about the recurrence, I think that the best way for us to learn about the trees problems, because it will teach us how to use the base case and the recurrence relation effectively. Let's go back to our problem, and then so in here the base case as defined in here, whenever we reach to the leaf node, which is with the left and the right is node, and then we can just return it directly to the parent node. And so in here we can divide the problem into the smaller problem. For example, in here we need to flatten the tree, right? And then it means that we need to flatten it for the left branch and for the right branch. Okay, so for each branch, and then we will have the subtree or the smaller tree, and then we will divide the problem into the smaller problem like that. So in here it is visualized by using the flatten root.left and flatten root.right. It means that we divide the data in the problem into a smaller problem by the subtree, right? Okay, so what is the current relations in here? So let's say that we are in the base K, and then we can see that this is the subtree. And then so in here the base K is solved. In here we reach to the base case, and then we return the node to the parent. We return the node for the parent. However, in here I introduce one thing, that is using the last node in each branch. This is the last node. It means that in here 3 is the last node on the left branch, while the 4 is the last node on the right branch, right, of the subtree. Okay, so when we reach to the left node and the right node, and then so what should we do? So in here, when we see that based on the requirement of the problem, and then we need to order it in the pre-order traverse. So here you can see that that is the root, right? And this is the left node, and this is the right node. Okay, so the thing in here is that remember, this one is the last node, and this one is the last node on the left, while this one is the last node on the right. This will be efficient for us to perform the future step. However, in this step, we can see that if this one is the last node on the left, what should we do? So it means that last node on the left, we can construct the thing we can put last node on the left in here. It will go to the first node on the right. Okay, so how can we do this? We do this by doing the things we will perform that left node dot right equals to node dot right. It means that we assign all of the branch. That we assign the right branch to the left branch in this case. And then what is the next step? And then we just need to get the node dot right equal to node dot left, right? It means that for now the node dot left, it will contain the value of the right as well. So for now we will construct by you point this right branch to the node dot left. It means that we change the branch, and then it results in this case. However, we have the critical point in here. It means that why do we just consider the last node? In here you can see that if for now what should we do in the next iteration, or what's now, because this one is the recurrence, right? And then we always just interested in returning the last node for now, because the last node is the right node, right? Because we point the left node to the right node. So for now the last node is for the subtree in here, that is the right node, right? The last node of the right node. Otherwise if if this one is empty, so it means that the last node is like the last node on the left. Okay, so for now our start is to do the similar thing. We will point this one here, right, and move the branch from this one to this one. Okay, so it means that like we move the first thing we can have assign this node to this node, and then we will assign this node to this node, right? So it means that we can form a new tree based on this one without using the stack. Okay, so let's implement it together. Okay, yeah, in here we have the for the base case, for example, like this, I mean the exception. So if the root is none, and then somehow we need to return it directly without doing anything. However, like if in here, like because like we traverse to all of the nodes in here, of course that is like the DFS, right? Depth search, and yeah, so we just define the DFS for the root, and the DFS here, it means that the flatten in here, I mean that is the flatten in here. I will use that is just a DFS to depict for the algorithm used. Yeah, so for firstly we will get the base case. So if the root dot left is none, and the root dot right is none, and then we just return it, return the root, right? This is our base case. And how is the recurrent relation? And then we just define the recurrence relation. Okay, so this is overall, right? Firstly, we get the left node is like the none, then the right node, it is the none as well initially, and we initialize all of the value. So okay, so what if the left node is not null, and then what should we do? So it means that like root dot left, right? If it is not null, it means that like we will get the last node on the left, right? So how can we do this? We just like get the left node will be equal to the DFS, right? And then we pass the root dot left. And because like we divide the problem into the smaller problem in here, eventually we will get the last node on the left. Yeah, so that is the on the right, and then we do the induction. So for this induction, like if the sorry, we need to do for the right as well. If the right node is not null, and then okay, so we will get the last node on the right. This diagonal left branch, right branch. Okay, so we do the same thing, that is equal to DFS dot root dot right, right? So for now we have the like last node on the left, last node on the right, and then what should we do? So we will do the induction by it means that we are in the level of the parents in here. So we will just like doing the induction. Yeah, so for now induction, it means that the relations was to return to the maybe the former parent. Yeah, so if the left node, and then it means that if the left node is not empty, and then we will get the left node equal to left node dot right, right, equal to the root dot right. So it means that we assign 3 in here to 4, and then we will get the root dot right equal to root dot left. It means that we transform the 2 to 3 in here. It includes all of the branches, and then we will get the root dot left equal to none, right? Because like yeah, when we replace this one, we move the all of the branch to the right hand side, and then all the things in here would be none, right? Is there's nothing on the left hand side of the value of 2. So this operation makes sure that. Okay, so for now we need to return the last node to the parents. Okay, so if the right node, right, if the right node is not none, so it means that we have some value in here. Otherwise, like, yeah, we just return the right node. Otherwise we will return the left node anyway, and then we just need to get the DFS for the root. Okay, so let's do, just check. Okay, so just check it works, right? Okay, just submit. Okay, so I think it is still good. And then, so yeah, I hope that this solution is useful for you. And yeah, so I think that like the tree, that is very important for us to learn about the recurrence. And also like that is the, maybe I think that like the very important step for us before we learn about the dynamic programming or other things related to the recurrence, because it will draw the mind map in our head that, okay, so how can it relate to the next level, and how can we return the values for the previous state or the formal levels. Okay, so I think that that is pretty much everything for our today problem, and I hope that you like this video. If you like my video, please give me a subscribe or the comment, because that is the motivations for me to continue to make the videos for you guys in the future. Yeah, so yeah, thank you so much for watching my video, and see you next time.